All right, so last time we finished our discussion over linear correlation and linear regression. And so what I put on the whiteboard here is some data, earnings of men and women. We have paired data, and it consists of median weekly earnings in dollars for male and female workers. We have a random sample of 6 jobs. So those of you watching the recording, you can go ahead and pause it and try the problem first, and then unpause and then see what the solution is. For those of you who are attending live, you've already had the opportunity to work on this. So what did you get for R when you plugged this in? What did you get for R? And you rounded to 3 places, right? Okay, good. All right, so for this one, R is going to be 0.853, you said? Yes, 0.853. Okay, good. This is our linear correlation coefficient. And the linear correlation coefficient R, that's what measures the strength of your linear relationship. Now, very important thing that I forgot to ask you on this problem is I forgot to ask you to graph this. You should always graph before you find the value of R. You should always see if there's a linear correlation. So you have to do a visual inspection, and the reason for that is because sometimes R will be high even though we don't have a linear correlation, maybe because when you look at your points, they are linear up to a point, but then maybe something else is happening. I don't know, something else that's, that's occurring, but there's part of those points that are linear. And so just because of that, your value of R may be strong. So you just have to be careful to make sure you look at the graph first. So that's what I would do in this case. I would look at the graph. So if you look at your graph, does there seem to be a linear trend here? Is there a linear correlation only based on your visual inspection? What do you say? Okay, so I have a no, so maybe not very clear. All right, so let me go ahead and show you what I have. So I am going to take you over to the calculator. And so now you should see the calculator on your desktop. So you went into Stat, hopefully, and enter, and then you just entered your data. Now I have data in L1 and L2, so of course you want to make sure you clear. All right, so in for L1, I'm going to go ahead and put my weekly earnings for men, and that's what's in X. So 695, 679, 672, 600, 418, and 700. All right, and then Y is going to be an L2, and that's my weekly earnings for women. All right, so if we're going to graph this, you have to turn your stat plot on, and that's second Y equals. Second Y equals. It should be on from last time. So my X's are in L1, my Y's are in L2. If you are on the on which is blinking, you have to select by pressing Enter. Make sure you select by pressing Enter. Anything that is blinking, just select it and you've entered it. You've selected it by pressing enter. So now I am going to go to Zoom and select number 9. Number 9 is Zoom Stat. So I just pressed the up arrow and it took me to the very bottom of the list. You could just select the down arrow and that takes you to Zoom Stat as well. Just look for Zoom Stat, and that's going to grab your data and plot it. And so that's where it is. Okay. So it looks like as you go from, as X gets larger, Y gets larger. Right, so it doesn't look a little linear to me. I don't know. It's not the best. Maybe if we changed our windows, it'll look better. Our range. If you go to Window, you can change your scale on your window, and that might be an option for you. It might look better. So you could always change the scale. If you go back to Graph, it goes back to that. So if in a different scale, it might look different. So we can go with that. It does seem to be linear. I'm not too sure though, but if you continue with your value of R, that'll help us. And so remember that if it's linear, we should be able to, there's a linear trend, which means as X increases, Y increases. And that's all the data points we have. So here's the first one and the last one. There's nothing after that. So to say that this might have a quadratic correlation, well, there's no other data points. It starts here and it ends here. And so as X increases, Y increases. So I'm going to go with the fact that I'm going to say that this is linear, right? There's a linear correlation here. Again, because there are no other points after this last one. It starts at the first one, ends at the last one, and there's some points in between. And so it looks like as X increases, so does Y. Okay, but still, if you're not sure, then that's why we go through the whole process. Now, sometimes it's very clear that it's not linear. So those are the ones where you want to, make sure that you make a note that okay, there's no way that this graph is linear. Then you can stop and say no, the graph does not have a linear correlation. But this one seems like we would be okay to continue. And again, if you're unsure, then you could always continue as well. All right, so R is 0.853. Okay, remember R measures the strength of a linear correlation. And so it asks if there's a significant linear correlation. So this is the part where you have to go through a hypothesis testing in order to find out if there's a significant linear correlation. Okay, so I'm going to just get a clean page here. And we have our first step is our null and our alternate. We have to set that up. And remember, for Chapter 10, linear regression and linear correlation, our parameter was rho. So it was equal to 0 and not equal to 0. So rho is RHO. That's our Greek letter rho. And when it equals 0, we say there's no significant linear correlation. But when it does not equal 0, we say that there is a significant linear correlation. And so that's our first step. And then our second step, we have our test statistic. Now there was two methods that I went over, method 1 and method 2. Here I'm referring to method 1. And when I do a linear regression t-test, it gives me all the information I need. So my test statistic is that's our t, and then our p-value would have also been given to me. And then from there we decide whether we reject or fail to reject the null hypothesis. So let me go ahead and go back to the calculator. Hopefully this is something you've already done. So I'm going to go to Stat and then over to Tests by using the right arrow key. And linear regression t-test, it's at the very end, so I'm going to go up instead of down, just because I'll get there faster. Linear regression t-test. And so my x's are in L1, my y's are in L2. The row is always not equal to 0. And just skip the regression equation, that stays blank. You're going to go to calculate. And so you're going to select, and there we go. That's the screen we should have all our information on. So we have our t, and we have our p-value. And if you scroll down, you'll find the r, which is what you guys gave me. All right, so I am going to take that value of t, and I'm going to write it here. It's a t, so we round to 3 places, so 3.272. 3.272. And our p-value is 0.0307. So I'm just copied that down. Okay, so our p-value seems to be less than alpha. And I don't think I gave you alpha. So anytime I do not give you alpha, then you assume it's 0.05. Okay, so if p-value is less than or equal to alpha, you reject, and that seems to be the case here. P-value is definitely less than 0.05. So we are going to reject the null hypothesis and look at what it says in the null hypothesis, that there is no significant linear correlation. So if I'm rejecting that, I'm going to cross it out. I just rejected it. So if we reject the null hypothesis, then the sample data supports what's in the alternate hypothesis. So there is a significant linear correlation. There is significant linear correlation. And only when there is a significant correlation can you use the regression equation to make predictions. And the regression equation, that was already given to you. All right, so look at the calculator. There it is. The y equals a plus bx at the top. A is your y-intercept, so if you scroll down, you'll have the values of a and b. A is the y-intercept and b is your slope. So I'm just taking those values, and that's going to give me my regression equation. And the only reason I'm writing it down right now is because there is a significant linear correlation. And so every time there is a significant linear correlation, I can use the regression equation to make predictions. So y hat is, it's a plus bx, it's 199.215, and b is 0.494 times x. All right, so I'm just using that model right there to write down my regression equation. So it's a plus bx. And now anytime you're asked to make predictions, you're going to go ahead and use that equation. And that's what the next part of this asks for. Well, it was there and then it disappeared. Okay, I was pretty sure I put it there. But there was a second part to this where I was asking you for the regression equation, and then I was asking you to make a prediction. I think it ended up going to the very end. So I asked you to make a prediction. What is happening when the male salary is $650? So predict female salary when male salary is $650 per week. So in our case, male salary, that's our X. So if you're trying to predict y when you're given x, and if there is a significant linear correlation, then you're going to use that regression equation. So you're going to use y hat for that. And so we have 199.215 plus 0.494 times our x, which is 650. And so that'll give you the predicted female salary. And I believe it's somewhere around 520. Now I'm going to see how I should round that. Y was they're up to the nearest dollar, so that's what I would do here. I would just round to the nearest dollar. So it looks like it probably would be $520. So you can use that regression equation to make predictions, but only if there's a significant linear correlation. All right, so that's a little bit of a review from last lecture. So again, here's the data that you are entering into your calculator. You should be able to graph the data. And sometimes it's clear that there's a linear correlation. Sometimes it's clear that there's definitely no linear correlation. And sometimes it's kind of unclear. All right, so only in the cases where it's very clear to you that there's no linear correlation can you stop and say there's no linear correlation here. Otherwise, if it looks like it might be linear and you're not real sure, then you just keep going. And in this case, there was enough evidence to show that there was a linear correlation. Okay, so that's a review of chapter 10. So again, you should be looking at the you should be going over the homework and making sure that you've been working on these problems. It helps right after a lecture to work on the new homework. So make sure you keep going to the homework section in My Stat Lab and make sure you're working on this homework. Very helpful to do it right after a lecture so you don't forget it. All right, so for today, what we're going to do, and then for the rest of our class meetings that we have, these are the sections that I'm going to concentrate on. So today, I'm looking at something called goodness of fit. Our next class meeting, we're going to go over something called contingency tables. And then the meeting after that, I'm going over something called ANOVA, which is analysis of variance. So this is a countdown to the last lectures of the semester. And ANOVA would be the last thing that's on your final exam. All right, so it's been quite a process of getting all the way down now to chapter 11. We started talking about inferential statistics in the middle of the semester when we talked about confidence intervals, and then we moved on to hypothesis testing. And when we first talked about that, we were only focusing on one population. And then quickly in chapter 9, we moved to 2 populations. And then in chapter 10, we're using paired data to see if there's a linear correlation among the paired data. And so we're continuing our discussion on inferential statistics. And in our last chapter, we're going to be testing using we're going to be testing using our chi-square distribution. We're going to come back and revisit our chi-square distribution. All right, so that was back table A4. So I'll have to pull that up. Okay, but we are going to be looking at hypothesis testing again, but this time our claim will make a statement about whether something occurs with equal frequencies or not. Okay, so we could think about that as our probabilities being equal when they talk about equal frequencies. All right, so we're going to be looking to see if we have something occurring with equal frequencies. All right, so we're going to focus on, let me go ahead and use my pointer. There it is. We're focusing on analysis of categorical data, and this categorical data is going to be separated into different categories. And these categories are called cells. Now, we are limited to qualitative. When we focus on analysis of categorical data, we're thinking of qualitative. And so we're going to separate this into different categories. So like, for example, Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, the days of the week, that would be qualitative, right? And so we're going to be using that to separate our data into different categories. So in that case, the days of the week were our categories. Okay, so our hypothesis test, it's observed counts that agree with some claimed distribution. So our hypothesis tests are going to be what's observed. It's our observed counts, and they agree with whatever's claimed. We're going to have a contingency table or a two-way frequency table, and it has 2 or more rows and columns. Okay, so we're going to be working with contingency tables. And more importantly, we're going to be using the chi-square distribution. So keep in mind that you're going to pull out that distribution back, that was table A4, and we're going to continue using that. Okay, so let me underline the main ideas here. We're going to start with the one-way frequency table. All right, we're going to start with the one-way frequency table. And we're going to use a hypothesis test for the claim that the observed frequencies agree with some claim distribution. So we always have a claim distribution, and we're going to see if what we are observing actually falls or actually behaves as what the claim is. Okay, so we will use a hypothesis test for the claim that the observed frequency counts agree with some claim distribution. And if it does, then there's a good fit of the observed data with the claim distribution. All right, so this is what we know as our goodness of fit test. So it's just a test that is used to test the hypothesis that an observed frequency distribution fits some claim distribution. So the observed frequency distribution fits some claim distribution. And you already know what frequencies are. We're counting how many times something happens. All right, so back from earlier chapters, we talked about frequencies, and it was just a count of how many times something occurred. So as far as our notation goes, here we have O, which is our observed frequency. This is what actually happens in our data. E is the expected frequency. This is what we would expect would happen if our observed follows that claim distribution. K represents the number of different categories. So if our categories are the days of the week, then we would have 7. K is the number of categories. And then N is the number of trials. Okay, so that's our new notation. And of course, we do have requirements as always. So our data is randomly selected. The sample data consists of frequency counts, and there are going to be frequency counts for each of the different categories. So for each category, the expected frequency has to be at least 5. All right, so there is a requirement for the expected frequency, but there's no requirement for the observed frequency. So although each category has to have an expected frequency that is at least 5, There is no requirement on the observed frequency, because observed, that's what's happening. So the data is what it is. We can't change it. Our observed frequency doesn't have a requirement. It is what it is. That's what's actually happening, what we actually see happening. But the expected frequency is at least 5. Now, what the expected frequency represents, this is the frequency that would occur if the data actually had the distribution that is being claimed. Okay, so hypothesis test is what we're going to go through. And in every hypothesis test we've been doing, there's been a test statistic. And so this is the test statistic that we are going to focus on. This is our new test statistic. And in this test statistic, notice that we are going to be summing. There's our summation here. All right, so this part right here, that tells us we're going to be adding up values. Here, the O's, those are the observed values. That's what actually happens. We get those from our data. And E, that's our expected values. Those are expected frequencies. So we have our observed frequencies, and we have our expected frequencies. So expected would happen, this is what we would expect would happen if we actually fall in that claim distribution. So you're going to take your observed values minus the expected values, get the difference between those two, square it, and divide by the expected value, or by the expected frequency. All right, so again, E is what we would expect would happen. That represents our expected frequency. And then O, this is what's actually in our data. That's what we observe. Okay, so that is our test statistic. And then our critical values, if we're using the traditional method of hypothesis testing, we're going to get our critical values from table A4. Remember, our test statistic starts with chi-squared, so that means we should be looking at table A4 when we get our critical values. K minus 1 degrees of freedom is what we're going to use. K is the number of categories. K is the number of categories. Now, a goodness of fit test is always right-tailed. A goodness of fit test is always right-tailed. So this has to do with the fact that either the O's are close to the E's, or they're not. All right? And so let me go ahead and show you. We have a graphic of that. But a goodness of fit test is always right-tailed. So either the observed are close to the expected frequencies or they're not. So they either fall in the shaded region or they don't. Now our p-values we're going to use our calculator to get our p-values, but you remember, just like before, if your p-value is less than or equal to alpha, we're going to reject the null hypothesis. So that hasn't changed, that's still the same. Now the way that we're going to calculate our expected frequencies, how we're going to calculate our expected frequencies is we're going to take n and divide it by the number of categories we have. So the sum of all our observed frequencies and divide that by the number of categories. So n is how many our total data. So total of all our observed frequencies. So if all expected frequencies are equal, that's how we're going to, that's the formula we're going to use. Now, if we're not assuming that expected frequencies are, if we're saying expected frequencies are not equal, then we would do something different. Okay, I'm going to come back to this because we're not using this right away. Right now, we're under the assumption that expected frequencies are all going to be equal. All right, and so we're going to come back to this one. But if they're not equal, then the calculation would be done in a different way. Okay, so this is a bit of an explanation of why we always have a right tail test. All right, so this is where it's written out for you, but sometimes it's better to look at a graph versus having to read a definition. So a close agreement between the observed and the expected values will lead to a small value of chi-squared, so your test statistic would be small, but you'd get a large p-value. So let me remind you what the test statistic was. Remember, the chi-squared test statistic, it was the O's minus the E's, and that would be squared, and that would be divided by E. Now, let me go ahead and change this a little bit because that summation needs to be a little bit bigger. So that was the test statistic I was talking about all the way over here. So you see how the sum is in front of that whole expression? So that's what I'm trying to get. Okay, there I am. So we're going to find out what O's minus E's are, observed minus the expected, square it and divide by the expected. Once we do that, we're going to add them all up. Okay, so if your O's and your E's are close, if your O's and your E's are close, I'm going to put that O as approximately E, then what happens is your denominator is going to be really small. You square it and you divide it by E, what's going to happen is you're going to get a small value of chi-squared. All right, so if your observed and the expected value are really close together, you're going to get a small value of a test statistic. Okay, but if your O and your E are far apart, I was going to write. Okay. If your O and your E are far apart, then there's a large disagreement between observed and expected values. So if your O and your E are far apart, there's going to be a large disagreement, right? So this will give you a large value of chi-squared. So you're going to get a large value. So a large value of chi-squared will end up with the small value of p. Okay, so remember that, small chi-squared, large p. So let's go back over here. So large chi-squared. So there's a large chi-squared. That means your chi-squared is on the right end. If you have a large chi-squared, that means you're on the right side. So this is what I'm talking about when we have a large chi-squared. And that's your observed and your expected are pretty far apart. So your observed is not what we would expect would happen. All right, so if your observed and your expected are far apart, you're going to get a large chi-squared value. And so you see that little area right here? Remember that the area that's shaded, that's your p-value? Well, that's going to give you a very small p-value. All right, so that's a very small p-value right there. That small area gives you a small p-value. And if you have a small p-value, you're going to reject the null hypothesis. Okay, but if your O's and your E's are close, that's going to give you a small chi-squared. And the small chi-squared is going to be somewhere to the left. And of course, if you look at that entire area, well, that area is large, and that's your p-value. So if your p-value is large, you're going to fail to reject the null hypothesis. All right, so when you look at the null hypothesis, let's see if I have it here. Okay, so the null hypothesis says that all your frequencies are the same. Now I put here all probabilities are equal You're talking about your frequencies. All frequencies are equal. So the null hypothesis says that they're all equal. All frequencies are equal, or all probabilities are equal. So the way we say that and it depends on how many we have, but they're all going to be equal. All right, so if they're all equal, the null hypothesis, we would fail to reject the null hypothesis, and that means that the observed values is what we would expect would happen. It fits our claim distribution. So if our O's and our E's are close, we're going to get a small chi-squared value, which in turn gives us a large p-value because this area is much larger. And so when we have a large p-value, we fail to reject the null hypothesis. Now the null hypothesis says that all our frequencies are equal, or all our probabilities are equal. So that means that our observed values and our expected values are close. So we are observing what we would expect would happen. And so we have a good fit with the assumed distribution. Now the nice thing about this is it never changes. Once you make the statement, the null will always have a statement about frequencies being equal or probabilities being equal. And the alternate would just say at least one of them is not the same. It's always going to be a right tail, always going to be a right tail using our chi-square distribution. And so when we calculate that test statistic, either the test statistic is going to be small or it's going to be large. If the O's and the E's are close, you're going to get a small test statistic, which in turn gives you a large p-value because the area is going to be larger. All right, so I'm going to come back to this. This is something we're going to be referencing. And so here's the process. Now remember, we're only going to focus right now on one row of data. And the null hypothesis is going to have a statement that all the probabilities are equal. And the alternate hypothesis then would have to say that at least one of them is different from the others. Not all of them are equal. Now there's a way of doing this on the calculator so you get a p-value. And I will show you that. But in case we want our critical value, well, we're going to get that from table A4. Okay. So I'm going to come back to this. These are the instructions of how to get our observed values in the calculator. And actually, I find that it's easier just to do it by hand and use the formula than to use the calculator on this one. But it's within your notes if you want to use that. Okay. So what kind of problem would you solve using this method? All right, so here's an example. It is a common belief that more fatal car crashes occur on certain days of the week, such as Friday or Saturday. We have a sample of motor vehicle deaths for a recent year in the state of Montana. So we have a random sample. The number of fatalities for the different days of the week are listed in the table. So our data is broken into different categories. And the number of categories here, that was our K. K was the number of categories. Test the claim that accidents occur with equal frequencies on the different days. All right, so just test the claim that accidents occur with equal frequency. So that means the probability of getting into an accident on Sunday is the same as the probability of getting into an accident on Monday, which is the same as Tuesday, Wednesday, and so on. So the probability of getting into an accident on any of the days is the same. That's what we would write in the null hypothesis. We're testing the claim that accidents occur with equal frequencies. So K is the number of categories. So notice that it's broken down, our data is broken down into 7 categories, the categories being the days of the week. What do you think N is equal to? All right, so you just add up all those numbers, right, to get N? Okay. So 180 is what you have. Okay. So remember that E is equal to N over K. So if accidents occur with equal frequencies, we would expect the same number of accidents on the different days, right? So what we see there are the observed values. So 31, 20, 20, 22, all these values that are on the table, those are known as our observed values. That's what actually happened. So what would we expect would happen if accidents occur with equal frequencies on the different days? Well, to find that out, you have to calculate what E is, and it would be N over K. So N was 180. That's our total number of fatalities, right? And then you divide that by the number of categories. So if you take 180 divided by 7, that would give you the number of fatalities that we would expect would occur if the accidents occur with equal frequencies on the different days. So did you get about 26? Okay. So what I'm going to, we could save this on the calculator. Yes, it does round to about 26. I'm just going to leave it just so that we know we want to make sure we need to be careful with our rounding. I'm going to keep it to about a couple of decimal places there. So about 0.71429, just to be careful with that. But we can go ahead and store that into our calculator. So about 26, yeah, so about 26, we would expect that if accidents occur with equal frequencies, then we would see about 26 every day, 26. So we're testing the claim that from this, given the sample, we're testing the claim that accidents occur with equal frequencies. So when we write down our null and our alternate hypothesis, the nice thing is it's never changing, it's always the same. So our null hypothesis will say that the probability of getting into an accident on each of the days would be the same. So our frequencies, we have equal frequencies, so that means our probability of getting into an accident on Sunday is the same as Monday, is the same as Tuesday, and so on. So we have probability of Sunday would equal the probability of Monday. So the probability of getting into an accident, they're the same. Sunday, Monday, Tuesday, Wednesday. Then we have Thursday, Friday, and then Saturday. All right. So that is what we write in the null hypothesis. The claim, again, is that the accidents occur with equal frequencies. So if they do occur with equal frequencies, that means that the probability of getting into an accident on the different days are the same. So the alternate hypothesis is just a statement that one of the probabilities is different. If at least one of the probability is different, then accidents do not occur with equal frequencies on the different days. So only one of them has to be different in order for the null hypothesis not to be true. At least one is different. So here we're trying to see if our observed frequencies follow a certain distribution. In this case, the distribution we're looking at is that goodness of fit, is that chi-square distribution. Okay, so our test statistic, that's our first step. We set up the null and the alternate. Our test statistic, we already know that. I'm going to go ahead and write it down. It is the sum of our observed minus our expected divided by our expected. And the numerator is squared. All right, so what we're doing here is you're taking your observed, which for Sunday it's 31, so you're going to take 31 minus what we would expect would happen. That's our expected value, and remember our expected value, that was the 180 over 7, which turned out to be 25.714, something like that. I'm going to keep it as a fraction. So expected was 180 over 7. Again, that's the one that turned out to be about 26. And so you're going to take the difference and you're going to square it, and then you're going to divide by the expected, which is the one that was about 26. But I'm leaving it as a fraction. And the summation means you're going to add. So the next observed is on Monday, which was 20. And so minus the expected value. And then that's going to get squared. And divide again by the expected frequency. And you're going to keep doing this. So that was Sunday, Monday, and you're going to do it again for Tuesday, Wednesday, Thursday, Friday, and then the last one I'm going to write here is for Saturday. So the observed value for Saturday is 36, and our expected, so our observed frequency was 36. Our expected frequency is the 26, which I'm writing as a fraction, 180 over 7. Remember that that is going to get squared. So you look at the difference between what you observe and what we would expect. You look at the difference, you square the difference, and then you divide it by the expected frequency. All right, so you're going to go ahead and do that for every category. And then you add them all up. And that's your test statistic. Okay, now that might seem like a lot of work. So as an alternative, there is a way of just putting in this data into your calculator, and then the calculator gives you a test statistic. But that's how the formula works. If you were going to use the formula for your test statistic, you would have to take every observed frequency, subtract the expected frequency, square it, and divide by the expected frequencies, and you would be adding all that up. Okay, so as an alternative, nice thing we have our calculator here, so I'm going to clear everything I have here. So we start with the new screen. There is something called the chi-square goodness of fit test. The chi-square goodness of fit test. And I'm going to take you there first so that you can see what it's asking us. So if you go to Stat, and then over to Tests. Of course, I have to enter my data, but we'll do that in just a minute. So go to Stat, and then over to Tests, and then just look for the chi-squared goodness of fit test. And I believe it's at the very bottom. So instead of going down, I'm just going to go up. and hopefully I find it and it's a little bit quicker. So there it is, the goodness of fit test. It's the chi-squared goodness of fit test. So I'm going to select that. And so we need to tell it where our observed frequencies are and our expected frequencies. So I need to put those in a list. Now, what do you think the degrees of freedom is going to be? Do you remember what degrees of freedom was here? All right, so it's k minus 1, right? So k was 7 categories. Okay, so 6. So degrees of freedom is k minus 1, k being the number of categories. We had 7 categories for the 7 days of the week. Okay, so 6. Now remember, I have to make sure that my observed values are in L1 and my expected values are in L2. All right, so before I do calculate, I'm just going to go to Stat, Edit, and I just want to make sure, again, that my observed values are in L1 and my expected are in L2. All right, so my observed go in L1. So if you remember those, we had 31, 20, 20, 22, 22, 29, and 36. Those are that's what actually happened in our sample. These are observed frequencies. So I would just go back and make sure no errors have been made in entering. All right, it looks good. Now, L2 is our expected frequencies, right? So that was always the same. That was 180 over 7, right? So that's going to be the same for all of these. 180 over 7. And I could have actually gone all the way up to the top of the list and just typed in 180 over 7 and would have made everything 180 over 7. So let me try that. That's a lot of work to have to type that in. Okay, so on here, I'm just going to try doing 180 over 7. See if it just makes that whole column 180 over 7. I don't know if it will. I'm just trying it out. No, it didn't like it. Okay, so it actually has to be one of the lists that you're using. It worked for some other things. Okay, so I actually have to type it in. All right, so I think I have them all in there. Okay, so 180 over 7, and my observed frequencies are in L1, and my expected frequencies are in L2. So I'm going to go back to Stat, over to Tests, and I was going up instead of down because that's at the bottom of the list, chi-squared goodness of fit test. There it is. And again, the observed ones were in L1 and the expected ones were in L2. So just make sure that they are where you put them. Okay, so on the word, over the word calculate, I'm just going to go and press enter. And there it is. I have my chi-squared value. That's our test statistic, and we have a p-value as well. Okay, so if anybody tried to use the formula here, you could verify that you're going to get the same test statistic. So if you continue here, you will notice that your chi-squared, your test statistic, is, what was it on the calculator? And I have to round it to how many places? How many places do we round chi-squared? Do you remember? Okay, so that would be 9.233. 3 places after the decimal, so 9.233. Okay, so that's our test statistic. And again, you can continue with this calculation up here, I just put plus dot dot dot. I didn't write them all down. But if you continue with all of these, plugging them in, and add them all up, you should end up with the same test statistic. Okay, so the other thing we have here, you have to decide whether we're going to do the p-value method or if you're going to do the traditional method. So you just have to decide which one it is. Here, I guess we can use the p-value method. So remember that the p-value, remember this is always a right-tail test. Okay, so if you're looking at the p-value method, and this is always a right-tail test, 9.233, that's our test statistic. So 9.233, that's our test statistic. So when I find the area to the right of 9.233, that's our p-value. And that's going to be a large p-value. So you can kind of get an idea of what's going to happen to your null hypothesis. So if we're finding the p-value, that's going to be the area to the right of 9.233, right? That's a pretty large area. All right, so if you were finding the p-value by hand, you would have to draw it out. The calculator gave us the p-value. And so we can go ahead and take that. And compare it to our value of alpha. All right, so using technology, we have our p-value, and I'm looking at the calculator here. It looks like the p-value is 0.160, and the 7 makes the 8 and 9. So 0.1609. That's our p-value. Okay, so is our p-value less than alpha? Did I give you alpha? I did not give you an alpha. So if I do not give you an alpha, what do you use? Okay, so there it is. 0.05 is what we use. So your p-value is definitely not less than alpha. All right, it's greater than alpha. So what does that say about your null hypothesis? So remember, we reject the null hypothesis when your p-value is less than alpha. And that was not our case here. Our p-value is not less than or equal to alpha. In fact, our p-value is greater than alpha. All right, so in this case, we're not rejecting the null. We failed to reject the null. We failed to reject the null hypothesis. So if we fail to reject the null hypothesis, do I still believe the null hypothesis? If I fail to reject it, do I still believe it? So I failed to reject the null hypothesis, so do I still assume that it's true? Okay, yeah. So if I fail to reject it, I still believe it, and I'm going to box it, and that's what I'm. So the data, there's not enough evidence to say otherwise. There's not enough evidence to say that we're going to reject our null hypothesis. So what does the null hypothesis say? It says that the probabilities of getting into an accident on all the different days are the same. So accidents occur with equal frequencies on the different days. So for this, you have to be aware that you can't just compare the values in your sample. You can clearly see that our values are different on the number of fatalities for Sunday, Monday, Tuesday, Wednesday, and so on. They're all different, well, except for, I guess, Monday and Tuesday, they were the same, and Wednesday and Thursday are the same. But if you're comparing them with each other, you could probably see that they're not all the same value. But that's not what we're talking about here. So we are using sample data to make predictions about what's happening in our population. So you have to make sure you go through a formal hypothesis test to see what we can predict about our population. So in this case, that evidence we have is not strong enough to reject the null hypothesis. So it's not enough, it's not strong enough for us to say that there's more accidents on certain days of the week. There's not enough evidence for us to say that some accidents occur with more frequencies, with higher frequencies on certain days of the week. We cannot say that. There's not enough evidence for that. Our evidence is not strong enough. So what I can say is that accidents occur with equal frequencies. They occur with equal frequencies on the different days. All right, and so that is what a hypothesis testing question is going to look like. Now, we are testing the claim to see if we have equal frequencies or if our probabilities are the same. That is the statement that goes in the null hypothesis. So either we have equal frequencies or we don't. And in this case, there's not enough evidence to say that we do not have equal frequencies. So we have to still assume that accidents occur with equal frequencies on the different days. So what you notice here is that I did use that chi-squared goodness of fit test on the calculator. That was the command. If I went to stat and tests, there's that goodness of fit test. So I'm going to write it up at the top here so you remember. We went to stat and then right arrow over to tests. And I used the chi-squared goodness of fit test. And that gave me my test statistic and the p-value. Now, if you were using the traditional method of hypothesis testing, then you would have to use your critical value. So let me get a new page. So if we were using the traditional method of hypothesis testing, our first step would be the same. And I'm just going to do ... And then I think we ended with Saturday. So the probability of getting into an accident on the different days are equal. And then our alternate hypothesis said that at least one is different. Our test statistic is the same one. I'm just copying it down. That's our 9.233. And if we are using the traditional method of hypothesis testing, you need a critical value. That's our CV. You need our critical value. You'll look at the distribution, which is from table A4. That's our chi-square distribution. It's always right-tailed. This one is always going to be right-tailed. And so I am looking for that critical value. Now remember, alpha is 0.05. So go ahead and get table A4, look up 0.05, and that's going to give you your critical value. Now, degrees of freedom, you already know what that is. All right, so here's the table I have on my desktop. That's my chi-square table, table A4, and here's 0.05. Remember, all of these areas give you a chi-squared value to the right. All those areas give you the chi-squared value to the right, the critical value of chi-squared. And our alpha was 0.05, and our degrees of freedom was 6. So it looks like that would be our critical value. So if degrees of freedom is 6, we are at 12.592. So 12.592. 12.592. All right, so then here's my test statistic. Does it fall in the shaded region, which is our critical region, or does it fall outside of our critical region? What do you say? Definitely outside, right? Yeah, because remember, this one starts at 0, so that 9.233 is to the left of 12.592. So it falls outside of the shaded region, so we would fail to reject. So if we fail to reject the null hypothesis, we still believe the null hypothesis. We still assume it's true. And what the null hypothesis says is that accidents occur with equal frequencies, that our probability of getting into an accident on all the different days, they're the same. All right, so there, accidents occur with equal frequencies on different days. And that, let me just put dot, 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 because it's the same conclusion as before. So you have the traditional method of hypothesis testing, and we have the p-value method, which is what I first went over. So the traditional method and the p-value method. Are there any questions? Okay, all right, so that is what this section is about. We're basically just testing claims that we have equal frequencies or we don't have equal frequencies. So, oh, that's where the rest of my problem went from chapter 10. Okay, so what I'm doing right now is I'm looking for some extra problems that I wanted you to use for practice. I had one in here in front of me, and then it just disappeared. Okay, so I am going to let me make sure I print out the participants list. Just I like to just have that record of who's attending live. All right, so today I'm looking to the lecture problems that are here. Okay, so I'm going to go ahead and give you the lecture problems. So for this lecture, this is our lecture 24. So you'll be able to see the questions that I'm going to ask you here. And I see it does not show up right now. All right, so it's not showing up right now, but it should be ready in about 5 minutes. It's not coming up. So I am going to go ahead and give you some questions dealing with this section, and that's going to be under homework. And the title of it is Lecture 24. All right, so I'm getting this ready. I want to remind you of a couple of things. The first thing is that your StatCrunch assignment, your second StatCrunch, is already on my StatLab. If you go to announcements, you'll see your second StatCrunch on there. So go ahead and open it up and make sure you read through it. If there are any questions, you need to let me know. You can post it on the discussion board. All right, so here's the one question I'm going to go ahead and put on your, so I found it. Okay, that's not it. It disappeared again. Okay, here it is. All right, so it says for a recent year, the following are numbers of homicides that occurred each month in a city. Use a 0.05 significance level to test the claim that homicides in a city are equally likely for each of the 12 months. So then the probability of a homicide in every month is the same. That is the null hypothesis, that P1 equals P2 equals P3 equals P4. Now there's a lot of those to write down. So you could just say all the homicides occur with equal frequencies on the different months. All right, so it's just that one question. And I had to reopen that because it wasn't publishing. But all right, so let me make sure it shows up. You have 3 attempts. And let me see if I can open it up now. All right, so okay, there it is. All right, so to get credit for watching this lecture, you want to make sure that you click on homework and then click on lecture 24, and there's just one question there. And that's the question I just talked about. All right, so for the null hypothesis, these are your options. All right, so remember the null hypothesis says that all frequencies are equal, or that all probabilities are equal. So you select the right one, and then you have options for the alternate hypothesis. Here your categories are the number of months. All right, so that is very similar to the one we just did. Okay, so make sure you do that problem before you log out or sometime before the deadline that I put on there. And then that's how you get credit for today's lecture. So I will talk to you next time as we continue chapter 11.